The watermarking is super aggressive too.
All right, so let's get started. So I have an aggressive presentation for you today. If you have explanatory questions, please ask them. If you have exploratory questions, please wait till the end. Is that clear, everyone? Does anyone need me to explain the explanatory? All right, we're good. All right, cool. So what I want to talk about today is systems design for people with better shit to do. So the first thing I'm going to do is let you know if you're a person who has better shit to do. So this is an awesome stock art rendering of a good engineer. So a good engineer is in the present day on the left, and she's trying to deliver some awesome feature or value or something. And in her way, it's this annoying technical problem, and she doesn't give a shit. She's focused on getting to the stuff on the right, because that's what her job actually is. Your job as an engineer is to deliver awesome products and functionality and solve problems to get to that. Your job is not to work on problems. Your job is not to crunch code all day. And this is a really important distinction that we'll talk more about. But to be an effective engineer, what it means to get more senior and better design and use your time more effectively is to find out how you can actually minimize the amount of time you spend working on annoying technical problems, because that's not your objective. And there's a slide for that. So yeah, this is your goal. And the whole point of this talk is to give you strategies and ways to think about how to achieve minimizing your time spent on annoying technical problems. So as I mentioned, this is a picture of a good engineer because she's focusing on getting to the right and she's not focusing on following. So I'm going to introduce a term that was invented by Joel Spolsky in 2001 of someone who's the opposite of this, someone who only cares about working on the code and solving technical problems, and they're focused on the wrong thing. And this term is an architecture astronaut. They're totally lost in the wrong sort of frame of reference. There's all these important things going down on Earth here, and the astronaut doesn't care. He's just I'm floating around space, and it's cool. And if all you care about as an engineer is writing clever code and spending all your time writing code, and you don't actually think about how do we deliver that value quickly and do more that matters, then you're an architecture astronaut. And I'll continue to use this guy throughout the talk as an example of spending too much of your time on the wrong thing. So how do we talk about minimizing time? So the sum of your time, if you think about building and maintaining a system, is the time you have to spend now building it and the time you have to spend later maintaining it. And when you're considering the design of a system, you need to think about both of those components to really figure out how do I minimize the amount of time I'm spending working on this system. And there are three basic pieces of slices you can put the complexity of a system into. The first is where we are all born, is that you don't know how to make a good system, and that's the boot. And then all the way on the right is the architecture astronaut. He's spending way too much time working on the system because that's actually what he wants to spend his time on, which is bad. You should be focusing on spending your time on delivering value to the customer and finishing the project and all of that stuff. And this is the happy sweet spot in the middle. It's kind of related to the probably apocryphal Einstein quote about as simple as possible and no simpler. So too far to the left, you haven't put enough thought into your system. It's too simple and it doesn't work. And in this middle area, that's the good spot where it's as simple as you could possibly make it, but it's still good and everything like that. So prepping for my work of publishing bullshit managerial tech books, I'm going to draw just an arbitrary curve on this graph. So if you think about building a system, this one's probably fairly intuitive. The more complex the system is, the longer it's going to take you to build it initially, right? So more complex, more effort. That's not very interesting. Now, it gets a little more interesting when you think about the time to maintain a system. So some people would have you say, well, we can spend a lot of time building a really elaborate, complex system now, and it will be so good and great that the maintenance costs over time will be lower the more time we spend on it now. So if we want to reduce our time spending on it forever, we should spend a lot of time working on this code now. And this is total bullshit. This is not correct. And the way this curve actually looks is more like this. So if you build something as simple as possible and no simpler, your maintenance cost is going to be as low as you can possibly get it because it's inherently simple. Simple is easier to maintain. I'm going to assert that as an axiom. If you don't believe that, we should have a talk later. And the reason systems end up getting built like this is the architecture astronaut in his heart of hearts actually wants to spend more time maintaining this in the future because this is the kind of shit he likes to do. The single best example of this, I think, in GameChanger history is dockets. So I know probably a lot of you aren't familiar with dockets, but basically in the early days of GameChanger, we built our own distributed queuing system on top of Redis, even though there were like 18 different off-the-shelf versions that would work perfectly well. And the reason we did that is because the engineers thought they'd be super clever and write some cool code, and they did, and then we had to maintain it for 4 years, and it was a disaster. So a lot of these systems, if you build them to the sort of limit of your technical knowledge and capability, they end up being really expensive to maintain, and you end up spending a lot of time on them going forward, which is bad because you should have better shit to do. So when you combine these curves, you get something that looks like this. So the total time you're going to spend on a system, which is time to build it and time to maintain it, is the sum of what we just talked about, and it's pretty obvious, like this is the sweet spot here if you have better shit to do. So what I'm going to talk about for the rest of the talk is how we can get a system to this point on the curve, ways to recognize when you're there, ways to think about how to get there, and the sort of the techniques that I go through when I'm designing a system. And just a side note, the way this usually works, this is, I say evolution of a systems programmer, but it's usually the evolution of a particular system as well. You start out not really knowing what you're doing, and then you learn enough to be dangerous. And now you are inadvertently, even if you do care about the right things, you're going to design stuff that looks like an architecture astronaut. And actually getting from knowing enough to be dangerous to knowing enough to be really good at your job is the part on the right, and this is the part I'm going to focus on. And I'm going to, for the rest of the talk, I'm going to run you through an actual system we've been designing. I'm going to talk about how I started out with a design that was very much in the astronaut phase, and I'm going to talk about how we got to a good design. So to set the stage, I'm going to talk about Sabretooth, obviously, because I'm Travis. So consider our current system. So what happens is you're at the game, you score an event, you get a legacy event, which, as I talked about in that Sabretooth talk, has all kinds of state baked on it, like lineup and play-by-play, fielders, and like everything you could ever want to go on this event. And so an event comes in and we tell our queues, like, hey, please go make this event process, please. And the way our queues work is we have a bunch of workers, and they just randomly grab stuff out of the queue. And any job can go to any worker. There's no like stateful coordination there, right? So these can bounce around. So worker 1 can be asked to process some events for game 1 and 2, and so can worker 2. So there's no real like method to the madness here. And this actually works fine in the old system. So the old system is order 1 in a lot of the operations we want to do. So I'm going to talk about calculating stats and processing meta events, which is how we do notifications. So stat engine 2, the old stat engine, it actually will snapshot it. Let's say it processes 300 events, and then it will snapshot itself and put a data in the database it can recover from, where it can say, I can just read this and get to the point where I look like after 300 events. And what that means is on the 301st event, all you need to do is load the snapshot and process 1 event. You don't have to process 301 events. Everyone follow that? So the old stat processing is basically order 1, because you're doing a snapshot and 1 event, and you're not doing 301 events. So that's a pretty good fit for just randomly sending stuff to workers, because any worker can get it, and it's a quick operation. Similarly, for meta event, each event has enough data, more or less, for us to send notifications about that event. So you can send event 301 to a worker, and it doesn't even need to care about the other 300 events, because there's enough data just on that event to do the same. So that's also order 1. Good. So Sabretooth.
Just a quick clarification. SE2 did that for every single event?
The snapshot is a little more complicated, but basically.
Okay.
So like I think on average, a stat engine 2 calculation has to read like 4 events or something.
Okay.
With some context. So Sabretooth is not as good at doing this in order 1 way. So Sabretooth does not snapshot itself. So if you send event 301 to Sabretooth, it actually needs to do 301 event processing steps to tell you what the stats are at that point. Similarly, these Sabretooth events do not have any state on them, really. So if you want to send, if you get a Sabretooth event that's a home run, in the legacy format, it will be like, it's a home run, and here's who hit it, and here's the score, and all that stuff, and you can make an event from that. All Sabretooth says is, there's a home run, which means you need to process those 301 events to figure out who hit the home run, what the score was, and all of that. So anything Sabretooth wants to do, because we've made it stateless, it's an order n operation. And what this means is that Sabretooth is a really bad fit for our current queuing architecture. Because if I sync a bunch of stuff from game 1, and those just get sent to random workers, if worker 1 gets event 300, it will do 300 computation steps. And then if you send the next one to worker 2, it will do 301 computation steps. And there's a lot of wasted effort, and it's really slow, and its order n, which is bad. Clear on that? So Sabertooth plus our current queuing system equals slow piece of shit. Because order n is really bad. And so what we're going to try to do now is we're going to work through building a system that's going to turn this order n operation into an order 1 operation. So the first thing I want to do is set like a basic theoretical framework for how I approach designing a system. So step 1 designing a system is you have to imagine what your system is going to do. And this is distinct from how your system is going to do it. So you have to like come up with a paradigm or like a design objective. I need to build a system that does this kind of thing. Step 1. Step 2 is what I'm going to call sketching. So once you know what you want to do, so say I want to draw an owl, you start with a sketch where it's like, yeah, like this theoretically, technically does what I want, and you need to realize your sketch is going to be bad, and that's totally fine. The idea is to get something on paper that accomplishes what you were trying to do, and then you're going to iterate on that, which is the next step, which is called refinement. So once you have a sketch, it works, but it's total dog shit, and that's totally normal. It's like a natural part of the design process. No matter how good you are, your first step is to make something that sucks. And then you want to go through, take that design, and without totally throwing it away, take little pieces of it, make it simpler, rip things out, and then at the end, you have an actual good design. So you've taken that sketch to its logical conclusion. And then the last thing you're going to do, this is one possible design to fix the problem that you came up with. So once you have a refined design, you actually have to look at it and say, okay, now that I've made this as good as I can make it, is it actually good? Or do I need to do this whole process again with a different paradigm? So like maybe I do this awesome owl, but I actually want to draw a cute little owl, and I need to start the whole thing again. And having the sort of like mental clarity to be able to like recognize these things along the way, so like recognizing that it's okay your first attempt sucks. Recognizing that if you take an attempt to its logical conclusion and it still sucks, you can start over. That's all necessary parts of coming up with a good design. So I'm going to start diving into these with our example. So step 1 is to think about a solution that could possibly solve your problem, and the idea is to focus on what such a solution would do, not how to do it. And the reason you want to approach it that way is because you want to be in sort of like a positive thinking mode. If you're thinking at this stage, oh, well, I can't do that because it's hard, or it's like, well, we shouldn't do that, you're going to be in this endless cycle of just doubting yourself, and you're supposed to push that off to later. So the framework I like to use for this is called divine design. The idea is if you imagine in your head like an omnipotent being for which any level of coding or complexity is just trivial, it's like not a problem. And you say, how would that omnipotent being design the thing? It's like a logical shortcut you can take to make you not focus on how to do stuff. So like the idea is to focus on what. It's like, what would a great system for this do? And this applies not only to like distributed systems design, it applies to API design. Like, what would a good API look like from the perspective of someone using it? Don't think about how it works. That's like a thing to deal with later. Like the first thing you got to do is figure out like what's like the best thing this can possibly do, and then later on you'll try to get to like how to actually implement that. And yeah, the idea is to separate the what of the system from the how of the system. So in our Sabertooth example, I came up with like a couple like high-level bullet points for what this thing has to do. So the main thing it has to do, like the thing we're trying to achieve for our customers, it's going to deliver highly available, real-time game data, which means it can't be slow as shit. Right? The next thing I came up with, this is a constant for everything we do on the platform team because it's really important, especially with such a small team that our stuff is like very maintainable. It needs to be easy to work with. So we're not going to have some insane, complicated XML SOAP interface or whatever. It's going to be HTTP call or like the library that we make to interface with it. This one's like kind of a throwaway, but like let's not like right now our peak games are like 5,000 games at a time probably. So like this thing should probably be able to handle like 15,000 at least. Does it need to handle like 1 million games at a time? No. Like if we ever get to that scale, we can deal with it later. Don't feel like you have to like solve the next decade's problems at every point along the way. And this last point I kind of buried the lead here, but this is really, really important. Anytime you're designing a system, unless like the fate of humanity or life and death are involved, make sure your design does not require humans. So like if you come up with a great design, it's like, oh yeah, and then just like, you know, if this happens, someone has to step in and run these commands and like do this recovery thing. It's like, that's not actually a design. It's definitely not a good design for like our kind of company. We don't have like dedicated ops people that can just do that kind of thing. So it's important to say ahead of time, like the what of this system is not going to involve human activity. And that's it. Like this step's really simple. There's no details here. It's just like, what is this actually going to do? So now we're going to start getting into actually how our system's going to work. So this is the sketching phase. So what we want to do in the sketching phase is we're going to turn our what into a how. We're actually going to come up with a concrete implementation where it's like, here's a way this could work. And again, it's kind of hard to think about everything all at once. You want to scope it down a little. Like the first thing you should be thinking about is like the main objective of the thing. So get something on paper that delivers highly available like real-time data. And if it's a pain in the ass to work with, we're going to deal with that in step 3. Like just focus on getting something that like technically works. And again, the most important like part of doing this is to just accept that your first attempt's going to suck no matter how good you are. And that's a natural part of the process. So I'm going to walk through designing a system that totally sucks, and then we'll talk about it. So the first thing to do when you're thinking about like how something's going to work is you need to come up with a basic paradigm for how you can solve your main problem. So our main problem was if you send random games to random workers, then they have to do a bunch of rework because they have to process 300 events over here and then 301 events over here. So the basic paradigm I'm going to go for is, hey, what if the one that did the 300 could just then do the 301, and if you kept that in memory between your runs, then it's order 1 all of a sudden. So in Sketch, like something over here is not a queue, whatever, but somehow worker 1 gets all the stuff for game 1 and can keep it in memory over the runs. And worker 2 can get all the stuff for game 2. And if we had something that did this, we would take our problem from order n to order 1. So processing one event would say, go take the server that already has all the other events and just do this extra one. So that's like the big idea of the design we're going to do. Is that clear? Seeing nods? All right. So now we're actually going to start sketching this out. So the first thing I'm going to do is I'm going to take this and I'm going to change it into this. So there's something on the left that routes games to specific workers, right? That's our paradigm. Like game 1 always goes to worker 1 because worker 1 will keep it in state between runs, right? So put that on the board. So there's a router that takes specific games to specific workers. All right, so how does that like work though? So keep it really simple. So there's obviously some sort of like table that or something that actually holds that mapping. If game 1 goes to worker 1, something has to know that game 1 goes to worker 1. So again, it's our sketch. We don't have to focus on like making this good or anything. Let's say if I technically had something that did this, and for every game that had a reference to the worker, that would work good enough. So I've got a routing table that lives here in the ethos somewhere, as Alex would say. And so that probably can't just live in like the electricity flying between the computers or something. So that's probably in some sort of like actual component of the system. And once you get to a point in your sketch where something looks like a database, or it looks like something that needs to like persist something across state, or it looks like something that's a like coordinated system, that's when you should probably start saying like, okay, I'm probably going to use something off the shelf for this. Like I'm not going to write my own database. So I've got a routing table and it's in some database-y thing. And now I need to think about what I'm really going to be doing with that routing table. So obviously the routing table holds the routes, so it needs to like store data, right? But how is that routing table going to get updated? So if you imagine this is like a living system, there are a couple things that are going to require my routing table to be updated. If a new game starts and my routing table is game to worker, someone needs to write that row that says this game goes to this worker. If I have game 1 going to worker 1 and and worker 1 dies, I should probably make game 1 go somewhere else. Because again, I want to deliver like an available game stats experience to my people. So if the workers die, I need to update the table. I also don't want this thing to require humans. So that means that our workers are going to auto-scale, like all of our stuff does. So if worker 8 shows up, how is that handled? Do I need to like balance some load across the workers? Do I need to send new guys to worker 8? Like, I need to know when workers go away, when they come back, and I need to know when new games happen. And that's going to inform my decision for these question marks. So whenever you come to one of these question mark points, this is where like having just knowledge of the ecosystem is helpful. One of the things that like I hear a lot from people is that I think there's like this perception that like knowing this is the most important like part of systems design, and it's important and it'll help you and it'll give you things to steal from other people, which we'll talk about. But like this is like the one part where that really matters. And if you're approaching your sketch in such a way that you know what you're looking for, so like I know I have to hold data and I have to like deal with these change events and like I have a pretty reasonable set of requirements, then you can just go around, look at what's available, and you can sort of imagine like how does this fit into this sketch? How does this fit into this sketch? And if skipping ahead, but if you iterate and realize that your first sketch was bad, this is actually a good point to come back to and say, okay, I chose this and I did a sketch and it's bad. What if I did this instead? So this is like a good divergence point. So for this problem, what I chose to use was Zookeeper. So Zookeeper is a sort of databasey kind of thing, but it's like headline thing is it does highly reliable distributed coordination. And what this is important for is those changes when the workers die and come back. So Zookeeper has 2 features that are really good for that kind of a flow. So the way a client interacts with Zookeeper is you make a persistent connection to Zookeeper. And Zookeeper can tell when you connect and when you like drop off. So if your box dies or you have a network partition, Zookeeper knows like, hey, that box just died. So it's really good for this sort of pattern where we're like, we need to adjust based on changes in our infrastructure. This is what Zookeepers use a lot for like health checking kind of stuff. It has these 2 features called ephemeral nodes. So I can connect to Zookeeper and say, write this file, and if I ever disconnect, delete that file. And then someone else can watch for those changes. So you can, by combining those, you can have something that says, hey, this worker just died, and Zookeeper just told me because I was watching that node's ephemeral node, and now I can do balancing stuff. So that's like kind of a lot of like very specific implementation with Zookeeper. But basically what I'm going to do is I'm going to use Zookeeper as my choice because it lets me take actions when boxes die. Just like that. So now I've got a design that looks like this. So I still have one remaining problem, which is that, okay, I kind of figured out how the routing table is going to change, but how does that actually like change? Like who does that? And I'm going to draw another box, and it's like this box is going to do that. So I have something else here. It's going to connect to Zookeeper, and when new games come in or when workers die or come back, you need to tell the routing table manager, and it's going to manage the routing table for you. And again, the idea here is not to get something simple. The idea is to get something down on paper that works. So to complete the sketch, I'm going to look at the 3 components I've just made, and I'm going to think about like what they actually do in this design I've made. So the first part is the router. So if you imagine it's an HTTP service talking to the sacred stuff, and you say, give me stats for this game. So the first thing your router has to do, it has to go ask Zookeeper, hey, like look in your routing table, where do I send this game? So that's get route. And if that comes back and it's good, then you send them along the way, right? So if that comes back and Zookeeper says, I don't know where to send that game, then you need to tell your routing manager, hey, I have a new game, could you please assign me a route? Right? So the router is like the ingestion point for the client's UP route. Which means if the router asks you to request a route, then the routing table manager needs to be able to assign routes and things. So that's something it has to do. Also, we talked about how we're going to deal with nodes connecting and disconnecting. So these specific workers are going to implement health checks into Zookeeper, where they connect and they say, hi, I'm here, please write this thing telling everyone I'm here, and if I ever go away, please delete that thing. That also means that when they do drop off, our routing table manager needs to check that out, and it needs to say, okay, worker 3 just died, I need to reassign all of the games that were going to worker 3, or else the system's going to go down.
Question about how the health check system works. Does it send a thing saying like, hey, I just died, or is it?
No, you maintain a persistent connection to Zookeeper.
Oh, okay.
And if that connection drops, then Zookeeper does stuff.
Got it. So it's not like it's checking for health checks every 3
No.
seconds or something.
No, it's actually, it's very scalable.
Okay.
This is why that feature is like the main reason I've chosen Zookeeper for this sketch. This also means that, let's say I have 10 workers going and I'm like drowning, and I add 10 more workers. Well, our games kind of start in like this pattern where it's like 9 o'clock, start a bunch of games, and then those will just be the games, and like 12 o'clock, start a bunch of games. So if I scale up in the middle of all these games, I wanted to actually use my new capacity, right? Like, that would be good. So my routing table manager needs to balance stuff now. So now I've got a balancer algorithm in here. And the other thing, as part of an available system, I don't want any of these to be single points of failure. So that means I'm going to need multiple routing table managers ready to go in case one of them dies. But I actually don't want both of them competing with each other, which means now I have leader elections to do, which is another feature that Zookeeper is pretty good at. But it's something else I have to do. So if I take these, and so this is like, here's my sketch. Here I need to build these 3 things, and they all need to do this. And this is how they communicate with each other. And that's a dashed line because the router doesn't actually talk directly to the table manager, they talk through Zookeeper, but they are talking to each other. So this is the sketch. And as I mentioned, this design is innovative. So this design has a lot of moving parts. I'm building 3 custom components. I have communication all over the place. And there's additional routing complexity that I'll get into that's just like not great. Like having one game go to one worker, not great. Technically works, but that doesn't scale very well. So I have a sketch here that technically works, and it's terrible, which means I've done a great job of sketching. So I have a sketch. Questions on the sketch? Or making a sketch?
Now, when you say sketch, you just like drew this. You didn't actually like build all this, or you did?
I haven't built anything.
Okay.
Alex is going to build it all.
In your sketching phase, are you pretty liberal with like when to draw boxes and when to introduce new actors into the system, and then you figure out how to simplify that?
Yes. The idea is to not limit yourself with problems yet. You want to like actually make a full system, and again acknowledge and accept the fact it's going to suck, because that doesn't actually matter. That's part of the process.
Is what you just said that sending a specific game to a specific worker is a bad idea?
So specifically what I meant is having a routing table with a row for every game is a bad idea because it does not scale well. And I have a lot of slides specifically on that that I'll do. Any other questions? Okay. So array R design is small, and that's totally fine. So the next step is we're going to take our terrible sketch design and we're going to refine that into something that's actually good. And there are a couple main strategies here that I always employ to like make my designs better. So the first one, if you've ever heard like me or Tom Leach open our mouths, you probably knew this was coming, is find the right abstraction. I'm going to get into more of what that means, but like generally there are patterns in software design that have solved the problem you're solving before, and you should use those because they're probably good. And that's related to the second point, which is steal rampantly. So this is another point where knowledge of the ecosystem comes into play, and not even in just like what's available. Like how does Mongo solve whatever problem? How does Zookeeper solve whatever problem? Because it's likely again that they've used these abstractions that you can also use to make your system better. And that applies in any domain. You know, if you're doing like crazy like HTML shit, like and you like learn how React does like weird DOM shit, maybe that's applicable to you. You can steal that, even if it's not like in using that itself. So like I'm going to use Zookeeper here, but I'm also going to use some ideas from Zookeeper in my other components. And the third strategy here is probably the single most important thing about being an effective engineer, and that's to be really dumb, very dumb. This is something that this is another thing that early GameChanger was terrible at. Like a lot of the early stuff we made it at our like absolute maximum level of like thought and capability. And the idea was like, I'm so smart, I can make this crazy complex system and make it work. And there's some like axiom with probably a fancy name where basically you have to be twice as smart to debug a system as you have to be to build it. So if you build something at your maximum level of thought, you're inherently not smart enough to debug it. Examples, Deck 2, Stat Engine 2, dockets, like a lot of our early stuff were built by smart people trying to build shit that only smart people could build, and the result was an unmaintainable disaster. And the way to get around that is to be really dumb. So take your design, anytime your design is doing something smart, it requires a lot of logic, try to make that really dumb. And I'll talk about ways to do that. And the last strategy for refining is squint a lot. So once you've made your design really dumb, oftentimes you can look at sort of the custom pieces you've made and say, you know what, if I just changed a little thing around here, that wouldn't have to be a custom piece anymore. And that lets you drastically reduce the scope of what you're building and use more off-the-shelf stuff. So I'm going to get into these now in our example. But first I'm going to consolidate the first three and steal the right dumb abstraction. And as I mentioned, this is where knowledge of the ecosystem is really helpful, just because you'll be introduced to patterns that people have used to solve similar problems to the problem you're solving now. So I'm going to look at our routing table and think about other ways people have solved problems similar to this and how we could apply them to our design.
Quick question.
Yep.
At this point in your process, have you written any lines of code?
No.
Just done research with the tools that you have available.
Yeah. This is beyond the scope of the talk, but basically, the general overview of how to design something, I think, is you go through this entire process and you have a design that you think is really solid and will work, and then you enter a validation phase where you start testing out some of those concepts concretely. We did that with Dusty. It's like we have a design, but like this works in theory, but like I don't really know how fast it is. I don't really know how far it will scale. Will this work with like 5 services, 10 services, 100 services? Like you'll have questions, and you should confront those in a specific validation step before you really go ham on writing the thing. Because you might learn that, hey, this looked good on paper, this actually sucks. But we're just going to focus on the first step of that today. It's just like getting the design. So let's start with this routing table. So in my sketch, I gave you the world's simplest routing table. There's a row for every game, and it says, I go to this worker. So if we plug an abstraction here to make this better, and that's bad because it's order n number of games. It doesn't scale very well because it's really big. And there's some like obvious abstractions we could apply here, and I'll talk about some of them. So what can we put between the games and the workers to like make this a little better? So the first thing, which should hopefully be obvious to anyone who's ever worked in a database that isn't MongoDB, is we kind of have 2 sets of objects here and they're related in some way. So maybe we could relate those better. Like we could have some sort of join to make the actual mapping of those a little more clear. So we could say, I have these 2 workers, and I have these 4 games, and I'll have like this logical set of workers over here, and the games will go to that like logical component, which will map to these workers. And the reason that might be a little better is if you imagine growing your worker set from 2 to 3, then you need to remap your space for that balancing algorithm we talked about. You need to reflect that in your routing table. So do you want to update like, a bunch of different rows, or do you want to like make that a little smaller and scalable and apply it on the right side of that joint where the cardinality of the workers is likely to be much lower than the cardinality of the games. You can even get really fancy here. And so notice this is a problem with, so I made this ring to represent like a whole hash space. So every game goes somewhere in this ring, right? And if you go from like 2 to 3, then if you do it naively, you end up bouncing a bunch of stuff around. Like notice that everything in ring 3 used to be in ring 2, and like ring 2 ate half of ring 1, but ring 1 is like totally fine, like nothing actually moved. So you can even employ strategies to be really efficient about this kind of moving. So this is called like consistent ring hashing, where you could get really smart about it and say, well, if my ring space grows, then I could cut it up into slices and make it so each part of that ring, instead of doing this, like where ring 1 is totally fine and ring 2 gets busted up, you could split it up so every ring gets fucked with equally, and you could make that work. And that was supposed to be really complicated and hard to understand because it's a terrible idea. Be really dumb. So if you come up with like a great idea that requires a lot of engineering power, it's very complicated, just like throw that away because it's terrible. So the absolute key to making good maintainable systems is to be really freaking stupid. So let's think about this routing problem like a more sort of formalized way. So big O is a thing that we all know about, and it's not only for like runtime complexity or like memory usage. Like you can actually think about sort of distributed system problem in sort of big O way. So let's look at our first example where the arrows represent sort of what our routing table is storing for us, right? So as our number of games grow, we're going to end up adding more of these routes. So that's order n in number of games. And order n, as we talked about, is bad. It doesn't scale super well, and it's complicated because things change. Like dealing with change is hard. This other system we started talking about, it's actually not really that much better. It's order n in the number of workers. There's additional complexity to rebalance stuff. And yeah, the cardinality is a little better, so it will scale better, but you're still having to deal with a lot of change. Change is hard. So what if we didn't have to deal with a lot of change? So let's do the same thing we did, and whenever we're doing benchmarking and trying to build something better, it's like, this is order n, let's make it order 1. Just apply that same thing to our routing problem. So, and just recall that order 1 means there's a constant cost. It doesn't mean that it's like 1 of n. It means that it's a constant cost. And constant is good because things that don't change are inherently similar to the things that do change. So how can we approach this routing problem and make it an order 1 problem? So first of all, let's make a large but unchanging number of routes. And I'll get to how we're going to map these. But let's say there's going to be 256 routes, like arrows, period, always. And again, because we're stealing rampantly here, let's take the nomenclature and let's call these virtual nodes, or V nodes. Which doesn't matter, but if you ever research it later, you'll find more stuff Googling that. And the way we're going to do the routing here with our static amount of routes is we're going to have many games, and a bunch of different games can go to the same virtual node. And for any given virtual node, you go to exactly 1 worker. So the number of games change, and the number of workers change, but the number of virtual nodes never change, and the number of routes never change. And we can think of a way we could do this. So if we take a random game, then what's important is that every game must deterministically map to a virtual node, because we don't want it to change. So let's say we have 256 V nodes, and imagine a world in which our games are integer ID. We could slap modulo on that, and we could say this game, for the entirety of its existence, will always go to virtual node 26. And what you don't have to know about for this part is what worker that's going to go to. Because that doesn't matter here. You're going to go to the same virtual node forever, which is simple. You're not looking up anything in a database. You're doing modulo on an IDE. So on this side of the equation, it's order 1 and the number of games. No matter how many games there are, looking out the route for 1 game is static, because that game is forever linked to 1 virtual node. So how does the other part of the equation work? Okay, so pretty straightforward. Every virtual node has to map to a worker, right? Because we want to get to that worker eventually. And the number of routes here will always be 256, because there are always 256 V nodes. Now the number of workers involved on the right hand of the equation is going to change. But the number of routes are going to be pretty static. And there will always be a route for a given V node, as long as you're keeping up with it. So on the right side of our equation, we're also order 1 in the number of workers. No matter how many workers there are, no matter how many games there are, they're exactly 256 routes, because you're routing between the V nodes and the workers. So you end up having something that looks like this, which is like really ugly and whatever, but there's a lot of V nodes, way more V nodes than workers. And as workers come in or as workers leave, you can adjust those same 256 routes to point to different workers, but people on the left hand of your equation don't care. They're just assuming that, hey, if I look for a V node, there's going to be a route there for me. And it's going to be the same V node for the same game forever. So let's take, given this design, which is an order 1 routing design, let's go back to what our routing table, our design actually has to do. And let's say if we have simplified the order n routing to an order 1 routing, what does this actually look like now?
Good question.
Yeah.
If you go to a particular V node, and and that vnode is mapped to potentially multiple workers. How do you what mechanism guarantees that it ends up on the same worker?
So the vnode, one vnode is going to be pegged to one worker at all times. And if that worker dies, we'll move it to a different worker.
So can you go back on that? Those 3 arrows go into the worker. It just means multiple vnodes,
Multiple vnodes.
can go to an individual worker.
Yes.
But it's never the other way around. It never works for multiple
Yes.
workers going to one vnode.
Yes. One vnode goes to one worker, but many of these can go to the same worker.
And if it gets remapped, if you bring up additional workers, so right now there are 3 going to worker 1. And now you bring up a worker 4, so one of those 3 vnodes gets pointed to worker 4.
Yes.
In that case, it would need to recalculate all 300 steps.
You would need to rebalance those same 256 routes. But the thing that gets simpler, which I'm about to get into, is that the people on the left don't care. And let's get into what it means that they don't care. So here's what our old system did. And now I'm going to start drawing lines through things that this abstraction lets us eliminate. Because remember, our objective is to get really dumb. So first of all, our old router had to look for a route. And if a specific game hadn't been routed yet, it had to communicate through Zookeeper into our manager that, hey, I need a route for this game. That does not happen anymore because the number of routes is static. So there will always be a route for a given vnode. And if there's always a route for a vnode, you never have to request a route. So not only have we eliminated that functionality from the router, we've eliminated one of the arrows, which are the most expensive pieces in any design. Like communication is hard. And if you can eliminate communication, that's great. So what else have we done with this design? Well, on the other side, because there are always 256 routes, we no longer have to unassign routes if a worker dies. We just need to balance things. So the balancing is still there, but we no longer have to like kill a route. There will always be 256 routes. Similarly, we never have to assign routes because there are always 256 routes. So all the extra work we were going to have to do every time a game came in, or every time a worker comes in, that's been reduced to when a new game comes in, we don't have to do anything because there's already a vnode for that game. And when the worker set changes, all we need to do is this balancing, which should probably be easier now because we have a static set of nodes we look at the balance. Probably not that difficult. So if we go back to our design, just from implementing this change, we've eliminated that arrow, which is huge. And each of these components has become significantly simpler. So this is our current design. And now we're going to enter the last strategy for refinement, which is splitting a lot. So if we go back and look at what our actual design does now, I want to focus on the router. So all this router does is you give it a vnode, and it needs to tell you what worker to send that vnode's games to. That's all it does. So the router gets a route for a specific vnode, and it goes to one of 256 routes that are always defined, and it will tell you this is the route, and then it can either forward it, or you can just go talk to that worker on your route. And right, here's my squinting graphic. So the idea is to squint at your components and say, hey, does this look like anything I can just do off the shelf? And that's what made it so simple. So, and again, if you think like, let's think like how we're going to talk to this. So, okay, we can make like an HTTP request, like an API, it's going to talk to the sabertooth thing, process some stuff, and give me some stats back. And if I want to focus on just this top line, so let's break that out a little more. So I have my client on the left, which is me writing sabertooth code, and it's going to go talk to the router and say, hey, where do I find vnode 3? The router's going to say, it's this worker, and then you go and talk to that specific worker. And like, when you're squinting, you kind of want to like generalize some. So maybe it's like, well, I'm thinking about workers, but they're actually HTTP. It doesn't really matter. Let's just think about like a server. So I have like a client, and there's like servers over here, and I want to get the specific servers, and I have the static set of routes. So like, maybe that would look like, I don't know, like sabertooth.vnode1.gc.com, and maybe that maps to a specific worker.gc.com. Like, it's kind of like what I've built here, right? And the idea of squinting is that you look at this and you say, oh, cool, I invented DNS. And if you can, here we didn't really have to make any changes, but if you can recognize that, like maybe I'm just really close to making DNS, or maybe I've already made DNS, then by going through the squinting exercise, you can further eliminate the amount of shit you have to build. and the amount of stuff that's in your system, and you can reduce your time for each curve. So if I go back to this and redraw my diagram, I actually added the client box to my main diagram, which wasn't there before. But now this looks much cleaner than my first attempt at this design. So I'm a save new client, and I want to process a game. I figure out the V node that game belongs to, and then I go look up the DNS for that game, which is like sabertooth.vnode1.gc.com, right? And then that DNS is just going to tell me, whoops, to go straight to the worker I care about. Now, totally out of band from the client, I don't need to communicate anymore to do this routing. Totally out of band to that, the workers are connected to Zookeeper just to let the manager know when they die. The DNS manager now, all it's doing is looking for workers that die and come on, and it's rebalancing the routing table, which is now in DNS. So instead of writing a bunch of custom shit, my OS is going to talk to DNS like it always does, right? And not only have I simplified this by the fact that I don't have to write a DNS server anymore, which is dumb, but from the client's perspective, this is an HTTP to a single URL that you like modulo and get to. And from the manager's perspective, also another point, I don't have to maintain my routing table in my database. I'm only using Zookeeper for health checks. Very simple. So, and if we take this view again, by using DNS instead of the router, I've gotten rid of all of this. So here's my final design. I have Zookeeper, which I'm only using for health checks. I have specific workers, which connect to Zookeeper only for health checks. And then I have this tiny little DNS manager box. All it does is balance 256 routes. Like, you could play code golf with that. It's probably like 10 lines of code. That's it. That's my entire design.
Still needs elections though?
Still needs elections because you want it to be highly available.
Oh, so you want more than one?
You want more than one, yeah. So once you've gone through this refinement exercise, and again, the keys are to be really dumb and to try to make your custom components fit the off-the-shelf stuff whenever possible. And once you've done this, and you can look at the design, and you're like, this is actually simple now. I can do this. Like, this isn't hard. That's generally your point to sit back, reflect on it, and say, is this design good now? Because it's possible the answer is no. It's possible you take a design to its logical conclusion, still sucks. Maybe you missed something. Maybe it's the wrong design. Maybe Zookeeper was the wrong choice. You need to sort of step back, look at the pros and cons of your design, do that validation exercise where you say, hey, I think this is going to work, and then you test it. It's like, oh, actually, this is totally shitty. And we've learned from some of our previous projects that, not only do you have to validate it, it's kind of tricky because you can run into things like, oh, this works in theory, but this driver totally sucks, and it's making everything break. There's shit like that you're going to run into. You're never going to catch everything, but stepping back, evaluating your design, and saying either I feel good going forward with this, or having the freedom to say, okay, no, actually this sucks, and I'm going to try something else. And this is something really good to use the rest of your team for. And there are various things that I'm sure reference Alex gave you about avoiding hive mind mentalities and all thinking about the same idea. If you have different people working on different sketches, and you're stealing ideas from different places, you're going to come up with different ideas, and you're going to be able to compare them and find something that really works. So that's the end of my presentation. I know that's a lot, and I guess what I was trying to get out there is a basic framework for thinking about these big, very complex problems. And again, the most important thing I think for me to communicate is that your first attempt will suck, and that's completely 100% fine. And you shouldn't feel bad about it. You should feel the opposite of bad about it. You should be like, I made something that works technically, and it's terrible, and that's fine. But recognizing it's okay to build on shit and turn it into something really good by these different ways of eliminating functionality, paring down custom components, and hopefully coming up with something at the end of the day that's going to minimize the amount of time you're spending writing fucking back-end saber-tooth processing architecture, maximizing your time delivering new game streams and better play-by-plays and stuff that actually matters. So that's it. So I will now take any questions.
What is the refresh time on DNS? I know when you do it through Amazon Web Console, it's not necessarily NVIDIA.
Yeah, so you can, first of all, that's a good thing you should validate. And you should bake those, whatever you find there, you need to make decisions like, is this latency acceptable? Is it not acceptable? How can we mitigate it? So there's a couple specific strategies you can do there. So first of all, there are more advanced DNS records you can use that are called service records that can actually hold multiple weighted routes. So you can imagine using a DNS configuration where you say, here's the DNS for vNode 1, the main node, the main worker for this node is this guy. But if you just tried to talk to him and he's either dead or you're partitioned or whatever, here's like 3 other things you can try.
Got it.
And that's like Alex sent me an article from Spotify where that's exactly what we did used to.
Yep.
But that's a good point. Like that's something you should validate.
Follow-up question, sort of, what, there's a trade-off between doing, like having a spin API where you send the game ID. If you ever just want to change from 256 to like 1024 or something, right? You'd have to change that everywhere in the code that you do that modulo thing,
Yeah.
rather than like a thin API that did that modulo in one place, right?
Yeah, you have to weigh the pros and cons there. Like in this particular example, I mean the modulo is literally that simple. You probably slap MD5 on top of it just to make sure you get some random distribution. But like versus running an actual service for that, no brainer. But it's definitely something to think about if it were more complicated.
Yeah.
But I think one of the things you can look at in design and say, is this design good? If it's something that's like so trivial that you're like, this is one line of code in like every major language, then like that's probably pretty good.
You made this sound very easy, which is a testament to.
So this process took me 3 weeks. When I'm designing new systems, I have a really hard time sleeping because as soon as I lie down to go to bed, my subconscious brain just like fucking tells my conscious brain to think about systems more. So it takes a really long time. Like Alex helps a lot, Jordan helps a lot when he's around, coming up with their own design. We bounce stuff around each other. It's not easy. I mean, I'm not trying to tell you it's easy. I'm trying to tell you it's achievable and giving you like ideas for how to approach these problems. And obviously, the more experienced engineers are like here to help and like bounce ideas off too.
So if a newbie wants to try to build confidence in this, is it best to try to just dive into the full process and design something, or should they try one phase and then build it out from like a mastery of one of those skills of one of the phases? How would you approach, or how would you advise someone who's never done any of it before to build a confidence in their own abilities?
So the first step is to acknowledge that like again it's completely fine to like come up with a bad design. Building a bad design is not completely fine, but that's not what we're talking about. We're talking about the thought stage. So one of the things that as a manager and as a senior engineer that I did a lot with Jordan when he was like starting out was I would go tell him, it's like, take like 4 hours or whatever and go design something to solve this problem. And I'd set expectations ahead of time. It's like, whatever you do is going to be bad, and we're going to talk about it, and that's totally fine. And like, set that expectation that it's like a learning exercise, and you're supposed to get better and learn, and then he'd come back, and I'd be like, that sucks, and that sucks, and that sucks. And then you try again, and I'd be like, okay, now you're down to one thing that's completely unacceptable. And I think on like the 4th or 5th try, I was like, yeah, that's really good. And I think just like setting expectations, giving people time to learn, and making sure that, kind of redundant, but like people feel okay, like talking about bad designs is totally fine. And if I don't know if any of you were here when Tom was here, but like there's no point in your career where you're just gonna have magically the best answer to everything on the first try. It's not coming. Actually, the opposite of that. Like there's the AllSpa article on being a senior engineer that I'll send around and everyone should read every couple months. Like this is like one of his biggest differentiators for being a senior engineer. It's like you realize that like your first attempts suck, and you ask people to like shoot holes in your design, and you like iterate on things. Because yeah, I mean like, could we have built the first design in this deck? Absolutely. We could have built it. It would have taken way longer. It would have sucked to maintain. We could have built it, and we would have felt super smart at the end of the day. But that doesn't make us good engineers. It makes us bad engineers. And the biggest step towards being a good engineer is like talking about the decisions, how to make them, why things suck, how things can be better, learning how other people solve hard problems, and applying them. So yeah, I'm not here to tell you it's easy. It's like not easy. It's really fucking hard. But part of like the support structure is enabling that learning.
Your initial sketching process, you drew a lot of boxes, and then went through the process of figuring out what are the responsibilities of all these things and why they have those responsibilities. That was an important step in validating some of the initial designs that you had. Do you usually go through that step every time, or do you ever find yourself short-circuiting and drawing it out in the diagram and initially saying, oh, immediately I can tell this is too complex, let me go try and simplify this before I even go down that path of validating my own design?
I actually think it's really important not to short circuit yourself. I'm trying to think of like every design I've ever made here has started out with some total dog shit on the whiteboard. Like the debouncer now is like 2 Redis calls, and my first design of that, like I built like a custom like buffer data structure that did just like insane shit, and I was really excited to build it because it was gonna be so fun and cool, but it was like absolutely terrible. But having like built that entire design let me actually think through parts of the problem that I wouldn't even have gotten to if I had short-circuited, and then those components of the problem can actually inform stuff earlier on. So I think if you short-circuit yourself, it's really easy to like never really come up with something, and it's really hard. Like I never would have gotten to this final design if I had short-circuited myself, because like getting to something that simple actually took like a lot of thinking about specifically why. Like take X property really sucks, and just thinking really hard about just that property. And this is basically the order I did things in, like the way I presented it. It's like when I had like a eureka moment about the static number of V nodes, and that led to all these other things. But if I had just stopped, I never would have gotten there. And maybe your brain was still in mind, but that's how I would. And it's also good for talking to other people on your team. If you have like a design that works all the way through, it's much easier because there aren't just like giant questions.